All right, welcome function folks to composition of functions. Day one. Yesterday we saw some ways to combine functions by adding and subtracting and multiplying them, and this is another way of combining them. But hopefully you tried the 3-minute review. This idea of we've got two functions. One is subtract 3 from twice the input, and g is square the input. And the question is does order matter? And hopefully you have tried this and you realize that the answer is yes, because you get a different answer if you do them in the other order. But let's see what we're talking about here. And I'm going to take, instead of you probably just tried some numbers, which is fine. Oh, you just tried the number 5, obviously. I'm going to actually do this algebraically. So f at x is what? Subtract 3 from twice the input. That's twice the input is 2x, subtract 3, and g at x is x squared. So I'm going to do f first. So that would be f at 5 is 2 times 5 minus 3. And that's 10 minus 3, which is 7. And then I'm going to do g to that, which is 7 squared, which is 49. Over here, if I did g first, then I'd have g at 5, which is 5 squared. And then I do f to it, 2 times 25 minus 3 is 50 minus 3, which is 47. They're not quite equal. They're pretty close, but they're not equal. So the answer here is, does order matter? Yes. They gave different answers. We got different answers. This idea of doing one function and then the next function is called composition. It's a new operation. And then right there it says at the bottom, this is composition of functions and is written as g composed with f at x. This is read as composed. Composed. G composed with f at x. And f composed with g at x. And this one goes with this question here. F is done to x first, so that it's like the right one is done first. Which is maybe a little bit opposite that you think, because we read from left to right, we think of the left one first, but it makes sense because it's closest to the f, right? So in this one, or closest to the x rather, g is closest to the x, it's done first. Let's see what this composition of functions business is all about here. And that's today's lesson. Expectations: determine functions that result from the composition of two functions and solve related problems. And so there's the 3-minute review question again, and I'm going to split this in half. All right. And so the idea here is, from a mapping diagram, if we had 5 first and then we did f to it, right? Well, f was subtract 3 from twice the input, we got 7, right? And then we did g to it, right? And we got 49. What we'd like to know is what the function would be that had an input of 5 and an output of 49. It's almost like a skip function. And that's what the composition of functions is all about. So let's think about this. If I started with any old input f, I ended up with, well, 2 times x minus 3, but I'm just going to think about this in general terms because I'm looking for a formula here. Then I get f at x, and then that becomes the input for g. Right? I do g to that, and it's g at f at x. It's kind of like f at x becomes the inside function. And this thing right here, that's the composition of functions. That's like the skip function. And we said that was f done first. Right? F was done first. And then that gives us our formula. It's g at f at x. And then over here, if I were to do the same thing, you can probably guess what's going to happen. That if I did g first, I got 25. And then once I did after that, I got 47. But of course, I'm more interested now in the formula, aren't I? This is g of x, and this is f. And then I take that input and I do f to it, f of g of x. And this skip function is another composition, a different composition. So this function that we did g first is f composed with g at x, and it is equal to, notice that the first thing is it becomes the inside function. That's the thing that's done first. And we read this as g composed with f at x, or sometimes we say of x. Good, and then on this one would be f composed with g of x. Of course, a natural thing to wonder, to think about, is are they the same? Is f composed with g equal to g composed with f? And if you think of it, well, it wasn't in the 3-minute review, so how can it be in general? And we'll see that the answer is no. And let's actually do this. So I'm going to do them match up with what we had f at first. Remember, we had f at x was 2x minus 3, and g at x was x squared. And I'm going to use this and actually calculate this, what this skip function would be, this new function. We said that f was the inside function. So we have g at, well, what was f at x was 2x minus 3. That's what that's equal to. But what's this g function? G is x squared. So whatever was in the spot of x, I put in what was ever on the inside here, 2x minus 3, and that's a new function, right? If I wanted to, I could expand this. This is 4x squared. 2 times negative 3 is negative 6, times 2 is negative 12x plus 9, and that is the composition function. That is the skip function. So I should, and I'm just going to check this just for funsies, if I have an input of 5, I should get an output of 49, because I did f to it first. I should, but let's check it out. And bing, 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 away on the calculator. That is 49, just like we expect. Now, what happens if we did the other way? Are we going to get, well, we're not going to get 49, we're going to get 47. That's what we saw. But let's do it algebraically. F composed with g at x is, well, the inside function is the one that's closest, f at g at x. So the inside function is x squared, right? There's g at x is x squared. And now in f, wherever the x was, I'm going to replace it with whatever's on the inside of the brackets. 2 times whatever minus 3, well, the whatever is x squared, and that's the new skip function. And notice, are they the same? No, they're not even close to them being the same. In fact, if I calculated what the 5 is there, I should get 50 minus 3 is 47, and they're different. But it's exactly what we would expect from before. So note, in this little equation, the domain of f is the range of g. So the output from here becomes the input for f, which is different than the operations before, where the domains had to match perfectly. wherever G is defined. So a little bit of a strange thing happens when we're thinking about the domain and range of the composition of functions. And we'll actually pick that little bit of business up in part 2 of the video.